Okay, I've switched the
This meeting
recording
is
on.
being recorded. Okay, I'll switch the recording on.
Okay, I think I should start, and
Okay,
um, you can interrupt me. Okay?
okay, please do.
Okay, please do.
Thank you, Martin. Thank you very much, and thank you, everybody, for joining me for this webinar. So I was asked to talk about quantitative research designs in business. Um, Basically, the difficult aspect of that is how much we can discuss. Quantitative research designs are so broad. There's a really wide range of different methods, models, and paradigms. So today, what I decided to do is to actually give you information about the new approaches, the new paradigms, and the new methods we're using, but also more importantly, how those are integrated with classical statistical methods. In the beginning, many people were wondering whether we should actually start exploring more advanced approaches to the existing statistical methods because that was the best approach, especially in business research. But soon people realized that many of the models we actually had were intractable in the end. So although we were approaching reality, we were not able to get simple models which would give us evidence to inform decision making. So the focus actually was shifted towards changing the paradigms instead and then trying to integrate the new paradigms with the existing statistical methods. The first thing we need to do is to establish the rationale. Why do we need quantitative analysis? And then consider paradigms and models, and then to see how they integrate with statistical methods. Very briefly, the reasoning is quite simply dealing with data, right? Trying to manipulate and manage the data, describe the data, and eventually analyze the data. Unlike qualitative research, quantitative approaches allow us to actually have a good, standardized, consistent, and systematic approach to data management, description, and analysis. This is important because obviously without a good data set, you cannot pursue any of the quantitative methods. The other aspect we need to clarify from the very beginning is really the probability premise, which is underlying any of the quantitative designs. We are dealing with uncertainty, with randomness, and therefore we need the probability construct. Probability is a numerical measure of how likely an event is to occur and is expressed between 0 and 1. The most important property, however, is how probability is going to allow us to actually have a representative, adequately representative sample. So we have the entire population, for example, customers of a very specific company, of a very specific business sector, and we want to try and get a sample which is going to be adequately representing the population. This is exactly what probability does. It allows us to actually get, through probability sampling, a very representative sample, which is going to allow us to generalize the results eventually. Now, we're going to explore the following paradigms. The first is the differentiation between parametric modeling and non-parametric modeling. Then classical statistics at the Bayesian rationality, which is new, a new paradigm. We're going to explore a little bit deterministic versus stochastic models, and finally, the debate between correlation and causation. Now, parametric implies a very well-known functional form of the distribution of the data, right? So we know the distribution of the data a priori. And this is really important because basically we can have a fixed number of estimable parameters and proceed. For example, multiple linear regression is like that. And the idea is that if you know the distribution, you will be able eventually to have a very efficient approach to your estimation. The non-parametric approach is very useful in business research at the moment because it doesn't assume that there is a very well-known distribution. The functional form is not known. In most cases, especially for small samples, not having to satisfy this strong assumption is really important. But in reality, only a few methods, non-parametric methods, actually appear to be tractable. Most of those methods eventually are leading to models which cannot be used in practice. They are so complex, which eventually are not useful for decision making. I also included here machine learning, which is very new. Obviously, machine learning deals with predictive models and latent variables which are we're not well aware of. Usually, they are psychological or behavioral variables, and we try to use to allow the model to teach itself basically along the way. So this is important because basically it simulates how the human brain functions. I'm going to explain this in a minute. So in terms of statistical methods, in the parametric category, we have the t-test, the linear regression, the logistic regression. The non-parametric, we have the chi-square test, the kernel density estimation. The kernel density, for example, is one of those cases where, although it's really fancy, it's really important, it can approach reality at the same time. It's so complex that we cannot use it eventually. Whereas the chi-square test is a very successful test in business research. And here I have an example just to demonstrate what I mean. The chi-square test for the null hypothesis whether or not customer satisfaction depends on conducting customer services support, as opposed to the alternative, customer satisfaction does depend on conducting support. So we have the null hypothesis that conducting support is not important for customer satisfaction, and we have the alternative that actually is important. We use the observations. We have 4 different pairs, obviously, 110 observations. And basically, the idea is to use the test, which is here, the formula, the O, the observed variable, the observed data, the E, the expected, what we expect, our expectations. We calculate the expectations based on this kind of formula, and eventually we get the chi-square statistic, and we compare it with the chi-square tables in order to make a decision. I'm not going to refer to all the details of the test because we're going to cover this a bit later, but just to see how a non-parametric test can actually inform the process of decision making in business. We can start with that as a stage 1 of the process, and then try to introduce a linear regression in order to check whether complaining is a statistical significance variable. But you can see why it is important, because with the chi-square test preceding allows us a better model specification going forward. And here we have the deep learning in the context of the neural networking I mentioned before, which simulates the brain, the human brain, basically, the different synapses of the neurons of the brain. Now, why is this important? Because basically we start with 4 different variables. We start exploring the causal relationships those may have with hidden layers of information, latent variables I mentioned before, things we are not aware of. We cannot include them as explanatory variables. And then we get so meaningful information about them that the neurons could actually allow us to reduce the dimensions and eventually get only 2 explanatory variables, whereas those will be particularly important for model specification going forward. And this is really the usefulness of those models, because it provides a much better model specification so that we can improve the statistical efficiency of classical statistics. Now, the new paradigm of Bayesian rationality, I consider it to be particularly important and influential for the future of business research. Although Bayes lived in the 18th century, his work was only published years after his death, and the applicability of Bayesian rationality in business has only taken place in the last 5-10 years, I would say. Unlike classical statistics, which treat probability as an objective entity, as a property of the world which we cannot influence, Bayesian rationality recognizes that actually our subjective beliefs could influence this process. And in reality, we're talking about our intuition, our emotions, and we all know that those do play a role when we are approaching a particular hypothesis or a particular variable, when we try to estimate those variables. In behavioral and psychological aspects, particularly when it comes to understanding customers in business, this is particularly important. The most important assumption is that people revise those beliefs according to the information and evidence they have available. So there is a subjective element of productivity, but obviously it does involve objective evidence as well. In order to revise your beliefs, you still need to deal with some objective evidence. And Bayesian rationality allows us basically to approach the statistical methods by using information from the past. Our past experience becomes important in order to understand what's going to happen in the future. Now, this also, although it's very important, it has some limitations. But before mentioning those limitations, let me give you an example of Bayesian rationality in business. What is a probability a customer will leave the company given that they just call customer support to complain? So we have, first of all, a conditional probability, right? Somebody is complaining. We want to try and find out what is the probability this customer is going to leave the company. The first thing we do is to identify relevant historical evidence, right? What do we know already? This is why it's important for a business to keep good records. 10% of customers leave in a typical period. This is something we know. We know also that 40% of customers who eventually leave had recently complained. This is something we know as well. 15% of all customers actually complain. So we have 3 pieces of information to use. We applied Bayes' theorem, which you can see here, the formula. And basically, by substituting the historical information, you calculate a new probability. This is a probability of leaving based on the fact that people actually complained. So we have a 26.7 probability, which compared to the attrition rate of 10% I mentioned before, the 10% here, you can see how all that is changing. Now, this is a good example where the departure point of the quantitative analysis is going to be different because you apply the Bayesian paradigm. We are using historical information to actually update our probabilities, and instead of using the 10%, you are using the most realistic, which is 26.7%, which is statistically is high enough, and therefore you can use this as an explanatory variable in regression. You can use, for example, the complaint when people want to complain as an actually explanatory variable, because you know this is influential. So basically, this idea is that we introduce the preliminary stage, which allows us a model specification which is much closer to the reality we experience, rather than having many explanatory variables, reducing the power of your model, and eventually many of those will be statistically insignificant. Now, the limitation I mentioned before is that when you actually depend on historical data, you are creating some sort of dependency on the past, right? You need the historical evidence in order to proceed. This could also act as a barrier to change going forward. So it would be important for a business manager or a leader to actually consider the best equilibrium point, to strike the best balance between the two. On one hand, we still need to learn from the past. On the other hand, we shouldn't allow the past to actually prevent us from exploring innovation, change, and developmental avenues. For that reason, when we reach that point, another approach, another paradigm, I would say, is the complex adaptive systems, complexity theory, basically, which the idea is simple. Basically, dealing with complexity means that we recognize that our business is dealing with many stakeholders at the same time. We are also dealing with many interactions, effects, many interrelations among those stakeholders. Therefore, it's really literally impossible to identify a number of explanatory variables which are going to help you during the analysis. For that reason, we introduce the complexity approach as the first stage of the process for better model specification going forward. Now, the idea is borrowed from life sciences and from physics in particular. You might have heard before the chaos theory, the butterfly effect. Those are important principles of complexity theory, because basically what we try to do is to recognize that even when we apply a very specific method of in statistics, we know that our business is going to go through change. Especially nowadays, this is happening all the time. So the idea is to try and contain the domino effect that's going to follow, the secondary changes, which could be unpredictable. And therefore, if we are in a position to do that, we're going to avoid chaos, but at the same time avoid stagnation. We still need to change, and we need to allow this to take place. In most cases, statistical methods will be invalidated at the same time, because change is going to change a lot of important parameters of our business. Therefore, what we need to do is to introduce a simulation model in the beginning to try and capture those parameters that are changing and they are important, and then use the information to specify the model we're going to follow in terms of the statistical method we're going to apply. Interestingly, this model was borrowed from the pandemic. During the pandemic, the COVID-19 pandemic, people used the SIR model, as we call it, in order to actually monitor the cases of COVID-19 based on the transmission rate of the illness. And people in business research realized that we can use this model exactly because it has been particularly effective during the pandemic. The applications, as you can see here, are various, although at a very, at its infancy at the moment. Customer adoption, product diffusion, viral marketing, spreading of information, spreading of computer viruses within the business, supply chain disruptions, etc. So this is basically the model, 3 differential equations, no time factor included. This is a restriction, but as I mentioned before, although it's simple in these terms, it is much better in terms of actually allowing us a tractable solution. Based on the pandemic experience, although it's not approaching reality in the way we would like it because of the absence of the time factor, it is still important because it's very beneficial in terms of outcomes. So what exactly we're doing, we have three variables: the sustainable, the infected, and the recovered, and we monitor their changes based on very specific parameters. The beta is the transmission rate, and gamma is the recovery rate. Let me give you an example in business just to demonstrate what I mean. Okay. Okay. Can you see the slides? Yeah, can you see the customer adoption slides? Thank you. Okay, so for susceptible, we can have potential customers, all candidates of actually adopting a new product. For the infected, we can have customers who actually adopt the product, and recovered customers who quit the product because of compromised loyalty. So you can see the relevance of the model, right? We want to monitor the susceptible, how much this is changing, whether susceptible actually are going to become infected, whether people who are good candidates to embrace the product, they actually adopt the product, and then how many of those are going to quit the product, or previously people who embrace the product, they are ready to quit. So we monitor all three of them, and what we try to do is eventually to consider, as you can see from this slide here, to consider how these three columns are developing every single day. It could be every week, it could be every month, depending on the time period you're choosing, to see how those equations are actually evolving. Because knowing one of them, the infected, you can also play around with S and R because they're all interrelated, as you can see. So you allow this programming to take place, and then you know the peak, you know when exactly you reach the maximum number of people who actually adopted the product. And you know at the same time whether your transmission rate and recovery rate, the rate according to which people actually adopt the product, and the rate which people are using in order to quit the product are changing along the way. If those are changing dramatically, it means that we need to include them as explanatory variables in a regression going forward. So instead of having a model with many different variables, you try to reduce immediately those variables, include the actual explanatory variables you want to monitor as the drivers of change within your company, and then you try to test those for statistical significance. It is much better because basically it allows you to observe what matters to the company and use that as the stage one of the process, and then try to specify your model with a smaller number of explanatory variables, which is going to improve your efficiency. So the SIR model is really important in these terms, but we can also use, and it's deterministic, as I said, which means it doesn't involve any aspects of randomness, of uncertainty. But there are stochastic models which are capable of actually introducing uncertainty, and we need to consider those as well. Some other deterministic you might be aware of are the break-even point formula, which deals with actual numbers, so there is no randomness. But those are really restrictive in terms of how they can help you in terms of informing a statistical method, whereas your stochastic models are actually more consistent with the randomness involved in statistical estimation. We have examples such as research on sales market demand, exchange rates, raw material prices, all of those are treated as random variables. Instead of predicting a very specific number, you are predicting a distribution. You say, for example, I can have 10,000 on average sales with a standard deviation of 2,000. So you are giving people a range, essentially, 8,000 towards 12. And this is much more realistic. And then using those models, the simulation actually allows you to become more specific, as I said before, and incorporate uncertainty and variability without, this is the key aspect, without increasing the number of explanatory variables substantially. This is really important for us because all of those statistical methods are weak only because we need to model a lot of explanatory variables, and we are missing many other variables, the confounding variables, as we're going to call them, which, although we don't model them, we know they're going to have an effect. So, using different paradigms as the stage one of the process allows us a much better specification going forward. Okay, another example of prescriptive models in the deterministic category are the decision trees and the optimization models. The simulation model is the SIR I just mentioned here, but the decision trees and the optimization models, although they are really important, you can see they are restrictive, but still in business research, we can use them to actually inform the second stage of the process. Decision tree, you can see an example here. Basically, you start with your strategy, you develop it in terms of the options you need, and then which levels of success or failure in order to estimate. Basically, you are pursuing a contingency scenario planning where you try to calculate expected outcomes, and then you estimate the net present value of those outcomes. So to compare the same units, and you compare them, and eventually you are in a position when you compare the different expected values to choose the highest as your product, the most important candidate for your product strategy. And then the next step will be, let's try and collect data and consider the statistical significance of that variable. So it simplifies your regression. You may have two independent variables rather than 4, 5, 6, 8 sometimes you can see in business research. The optimization model is a little bit restricted, but you can see their application in business journals a lot. Basically, we have the compound business growth. The compound interest, you might find, is exactly the same formula where you have a constant and you have the G being the growth rate, T is the year you are exploring. But basically, you can see it's deterministic. There is nothing random in that. You simply run the programming for every single year, and you are in a position to understand how your productivity or your sales are evolving. This is important because basically you understand your trends, and then you are in a better position to specify the model you want to test statistically. Okay, things you might be aware of already: descriptive statistics, the mean, the median, the mode, the median being the middle value, especially when we have extreme outliers which could invalidate the average. The measures of dispersion, the variance, the standard deviation, which is the square root of variance, the most important, how far away from the average our data are actually positioned on average. And eventually what we try to do is really to ensure that people are not using descriptive statistics for inference, okay? We are using descriptive statistics because we want to describe things. We don't want to actually derive conclusions based on those. Confidence interval is descriptive, right? You want to calculate using a very easy formula the upper and lower limit of the within the distribution where the true parameter of the population is actually going to fall under. But that's all you know. You know, the next step will be to try and specify the model you need in order to test what you want to test. And therefore, this is a preliminary stage. The same stands with the confusion between correlation and covariance. Covariance gives you information about how two variables are moving together, but only correlation is going to give you the strength of that relationship, how close those variables are. And again, that shouldn't be confused with causality, which means the cause and effect. We don't just know that two variables are moving together. We also know that one of them is actually influencing the other, which is very, very different. Okay, another element which is important in stage one of the process is time series analysis. Time series analysis is complex, and I'm not suggesting that you should pursuing models which are really complex in these terms. But there are models which have been proven to be particularly useful, and they are simple in business research. So we have random walk and random walk with a drift. Random walk simply means we start with a model which give us information about how much our sales this year depend on last year's sales. And then we have the epsilon term, which represents unobserved variables, unobserved factors. For example, nowadays we have the oil prices with a characterized by a very high variation. This is included here. It's something we cannot predict. It's exogenously given. It's like a shock. So we can model that and try to see exactly the dependency of every new year's sales on the previous years and try to really consider the trend. And based on that, you can make predictions. But more importantly, you can consider how you're going to specify the model in when you're using very specific methods in classical statistics. The random walk with the drift is similar, but it involves a constant which is associated with business change, basically, the structural factors of the business. It attempts to capture the actual trend of business development, right? So this is important because basically, although we have aspects we cannot control within the epsilon, we also have the delta, which means factors we can control, and they are associated with the change of the business, and therefore this is important because it can give you the upward or downward trend, which is exactly what you need in order to identify explanatory variables for your model specification going forward. And the proof for that is that nowadays energy economists around the world are using this particular model, the random walk with a drift, in energy economics. You can see that people try to model oil prices, try to understand the upward trend, continuously increasing prices, oil prices, and they are using this simple model. So this is a proof that the applicability of the model has something to say, and therefore we need to understand whether we can use this model as stage one of the estimation process and then proceed with a better model specification going forward. You can see here other applications. Risk management and financial planning in particular are very well-known applications of the random walk with a drift. Okay, another paradigm, another method within the context of stage one, introducing a preliminary stage before actually specifying statistical models, is a structural equation modeling. I'm not going to say much because this is a little bit more complex, but basically, if you are familiar with multiple regression, the new element is factor analysis. Factor analysis is an attempt to actually identify a set of preliminary themes, factors, which are influencing a particular problem, business problem. Usually we use literature review in order to get these factors. And then what we try to do is to reduce the dimension, to reduce the number of those factors by identifying commonalities among them. So there are many factors which are interrelated conceptually, right? And what this method attempts to do, the factor analysis, is to use correlation statistics. Pearson's correlation indicator is a very well known and reliable one, for example, to calculate the relationship, the closeness of those factors, and eventually reduce the number of factors to a much smaller number. And conceptually, however, each one of those eventual factors are going to be much broader, much more comprehensive and inclusive. I have an example here just to demonstrate. For example, I start with 3 initial factors and those are interrelated, so I reduce them down to 1, which is perceived quality. The same stands for customer expectations, and that's how I proceed with my causal relationship. So it simplifies things a lot. I can even have that at the end when you have a very specific outcome you want to test, but you also want to see whether that outcome actually is the primary outcome or is a derivative outcome. It depends on other variables which are hidden. So this is an important stage 1, again, in the process to try and better specify our statistical model. I mentioned already the difference between correlation and causation. Obviously, the most important for me is to remember that we cannot easily control confounders. Confounders means many important social, demographic, educational background, professional background, cultural elements, characteristics of people which might actually interfere with the statistical process, but we don't have, we cannot really act in order to control that. There are ways we can drop one variable and then try to consider interaction effects with a very specific socio-demographic characteristic, whether social class, for example, makes a difference, or educational level, etc. But really, it's very time consuming, very difficult. It affects the statistical power, is not the best approach. So what we try to do with those models I just referred to is to consider how we can improve statistical efficiency without having to go through those difficult activities. One really important state-of-the-art approach is the introduction of randomized controlled trials in business research. Randomized controlled trials have been used for many decades in medicine, in health sciences, in life sciences, and only recently people realized its usefulness in business research. Why do we need randomized controlled trials? The main aspect is randomization. Randomization means if you have 2 groups, if you have a very specific business strategy, a training course, and a very specific leadership style, right? You have a very specific new product you want to check, and you divide your customers into 2 groups. Basically, if you try to consider in observational terms the effects of that strategy, the effects of that product on both of those groups in order to make a decision about its importance, you are not going to get reliable results because there are so many other factors which might interfere in order to influence their decision-making process. So the confounding bias is there. The selection bias is there. How are you going to select people in order to divide them into 2 groups, one of them receiving the strategy, the other group not receiving the strategy? So randomization is critical, and that's why randomized controlled trials are really important because they are very, very rigorous. What exactly do we mean by randomization? Obviously, it means to follow a random approach in terms of the allocation, how you're going to assign people in the 2 groups. But the most important, and this is the key aspect people sometimes miss, is that randomization actually distributes the effects of socio-demographic characteristics evenly across among the two groups, right? So this is really the most important element. You don't have to worry about confounding factors anymore. The reason is very simple. You are neutralizes their effect eventually. You don't remove it, the effect overall, but you are neutralizing. So that means most of those impacts are going to cancel each other out exactly because of this randomization process. And that is very important for us when it comes to inferential statistics, right? A business example is how employee training could influence productivity, for example. Now, in the UK, um, there has been a very important randomized control trial, one of the largest and one of the first, I would say, that the UK government used to introduce um, uh, to try and make a decision whether or not subsidization, R&D, research and development subsidization is needed for startup businesses, moderate-sized businesses, in order to help them improve their productivity. Uh, I have the link here. This is a very important study because it demonstrated that actually randomized controlled trials could be very, very useful in business research. And people make decisions. Actually, they have proven that vouchers are important. They can make a difference for small, especially for small-sized companies. And the UK government proceeded to actually create a policy associated with this decision. It was a very important project run by the London School of Economics. I happen to actually know the people who prepared it, and I believe is one of the most influential, which is going to change how business research is taking place in the future. Okay, now I'm going to turn to focus a little bit on the experiments sides now and the associated surveys. So far, all of those discussions about conventional statistics and classical statistics are based on conventional surveys as well. By the way, the difference between a questionnaire and a survey involves questions which are interrelated. Yeah, usually every next question depends on the previous one in most cases. So surveys are telling us a story. A questionnaire usually includes autonomous questions. In most cases, people measure attitudes, opinions, self-reported preferences. People state the importance of those different dimensions, different factors. And in most cases, those conventional surveys are not really the best when it comes to causality. They are good in terms of correlation, not necessarily in terms of revealing causality between variables. So today I'm going to introduce you to the so-called discrete choice experiment. The discrete choice experiment attempts to um, to try and consider the reality, the complex reality of decision making. When we are choosing a product, let's say a package of biscuits at the supermarket, we are not thinking only about one factor, about the price, for example. We're thinking about the price, we're thinking about the healthy element, we're thinking about the taste, level of satisfaction, etc. So the packaging. So there are so many factors which we consider, and this is a key element, we consider simultaneously. We don't isolate them in order to make decisions. And usually we only need, seconds or a minute in order to make a decision. Complex decisions, but we only spend a very short period of time in order to actually derive a conclusion. Now, the discrete choice experiments are important precisely because um, they allow people to become a little bit more conscious of their preferences, the preference structure, how they formulate preferences, to try essentially and understand um, which dimensions, which attributes they prioritize in order to make a decision. Um, so I'm going to give you an example of a discrete choice experiment, but beforehand, let's see how the classical, the conventional survey questions have been developed over time. So we have here the semantic differential scale, where you have a continuum in terms of responding to the question, strongly disagree towards strongly agree. We have the Likert scale, which is discrete levels, right? And that's how you tick a box, basically. You can see those are really helpful still, but not always practical. For example, how are you going to differentiate those two levels in the middle when you're dealing with how empathetic a particular business manager is something that is very demanding overall. Um, and overall, we need to consider when we're designing a questionnaire, obviously, we need to consider what makes a good question. We need to be careful about the appropriate language we're going to use, avoid emotionally charged and culturally challenged terms, ensuring that we don't provide the answer to people within the question, ensuring the questions are clear, short, avoid cognitive burden for people. So all of those are really still important, particularly introducing semi-structured questions nowadays, because we do need people to choose in a structured way, tick a box, but we also need them to tell us why. So the context is important. So qualitative feedback is still important, very important, and that's why mixed methods in business research are becoming the norm at the moment. We still need to understand how people are making decisions. Obviously, you may not be able to use this kind of information in quantitative analysis, but you are going to use it during the interpretation of the results. And this is critical for us in statistical methods. So for discrete choice experiment, it's changing completely the paradigm. Why? As you can see here, I'm providing a discrete choice experiment, a choice set of an experiment for chocolate bars. So what is the difference here? We identify from a literature review or from a focus group, which are the attributes people consider. I have 7 of those for chocolate here: brand, price, cocoa strength, sugar, origin, nuts, and the ethical factor. Then I consider how many levels are important. Again, this is something you have to establish a priori from qualitative work. And here I have 4 brands, I have 4 prices, I have only 3 levels for sugar, I have only 1 for ethical. So it depends how you're going to structure those levels. Obviously, in a questionnaire, you may have 8, 10, 12 of those choice sets. And what we try to do is not to use all of the levels, but some of them. If I force somebody, force in quotes, to choose between those 2 brands, or Godiva and Dove, right, only, then that particular individual is going to force themselves to make a decision and prioritize which one would be preferable. And then in another choice set, I can compare those with other brands, and gradually I try to understand how this particular individual is actually valuing brand as an attribute during preference formulation. And if you keep repeating that, basically what you get, because people need to choose one option only for every choice set, you are getting a prioritization of attributes. You know which attributes are the most important or for the majority of the respondents, and then you are using only those as explanatory variables for your regression, for any statistical method you want to use, analysis of variance, for example. The discrete choice experiment, I consider it to be particularly important nowadays in business research, exactly because it allows us to approach reality, the complexity of decision making, right? As I said before, we consider simultaneously different factors in order to make a decision. Therefore, if you try to isolate those factors and ask people one at a time, you're not getting the whole picture. You're not getting the actual real-time picture. And this is exactly what you need. You need to approach the complexity of reality as much as possible. Now, when it comes to this aspect, we need to consider Bayesian rationality, because Bayesian rationality will help us for this discrete choice experiment. You can have a pilot discrete choice experiment to test essentially whether people actually prefer certain attributes or not. If you have 8 of those, you can reduce them down to 6 or 5 if you actually have a pilot questionnaire to validate what people think. Then you can have a pilot questionnaire and actually get more information about whether people consider this to be demanding in terms of comprehension. People are getting bored, so you can reduce the number of choices, etc. So the Bayesian approach allows us to have prior information as important of the process and then try to refine the main questionnaire going forward. Now, the problem, however, statistically, is the fact that we cannot approach the discrete choice experiment with a new survey in a linear form, because the logistic regression is not linear, as you can see the function here, is exponential. The chi appears as an exponent. So, and again, I mentioned before, this is not a line, it's not a regression line, it's an S-shaped curve, the sigmoid curve, as we call it. So that means essentially we need to do something in order to create a more tractable model. We are using the discrete choice experiment as the first stage of the process, and we try to introduce a linearization, taking natural logarithms in both of those parts of the equation. You can see how, if we do that, we can get a linear form of the equation. In the right-hand side, you can see this is linear. So now you can apply the multiple linear regression, right? And in the left-hand side, you can see this is a different dependent variable. And this is really what we need to be a little bit careful about, because now you don't have a continuous variable to be your dependent variable. You have discrete variables, categorical, qualitative dependent variables, which means you're going to have basically, if I want to use this example, you're going to have 4 different linear regressions where for each one you compare the probability of an individual choosing option 1 compared to doing nothing, the status quo, not purchasing a new chocolate bar, right? The second one will be comparing the probability of choosing option 2 as opposed to doing nothing, then probability of choosing option 3 as opposed to doing nothing, etc. So you have 4 linear regressions within one equation. This is exactly what we do with logistic regression. Our dependent variable is not continuous anymore, so we need to model it as a discrete variable. Option 1, 2, 3, 4, very discrete. We cannot quantify them easily. Now, the other element, which is important, is how once you get the multiple linear regression coefficient estimates, how you're going to interpret them. This is a little bit tricky because basically you can see here in the dependent variable, the left-hand side component, you do not have a probability. You have actually a ratio, probability divided by 1 minus probability. The probability of an event happening than not, basically, which is what we call in statistics the odds. The odds are a little bit more specific and much more demanding compared to probability. Therefore, we need to understand why and how we're going to interpret our coefficients. So if, for example, I have an estimation like this, the 0.4 is going to be the coefficient of my explanatory variable. And I'm using it with the exponent I had before, and I derive a number I need to do that before going back to interpret my coefficients, right? So on this occasion, I'm going to say the odds of option 1 are going to be 1.5 times more than doing nothing. So I'm preferring 1 times more option 1 compared to not purchasing any chocolate bars at the moment. I can demonstrate the strength of my preference basically. And this is important because this is not the probability, okay? This is the p divided by 1 minus p. And that's why we need to be careful with the interpretation. But honestly, in practice, when it comes to business problems, what we actually need is a comparison only, the strength of preference. If you have 1.5 to be option 1, 1.3 option 2, 1.1 to be option 3, obviously you understand that option 1 is the dominant option for that individual. And this is really all you need in order to derive conclusions. And then obviously consider on average all the individuals in your sample and try to make a decision. So logistic regression is really important because it involves an element of adaptive learning. We are teaching people how to proceed, how to actually discover their own preferences. Okay, I'm going to demonstrate now some classical statistical methods very briefly, and we're going to close the session. I included some of those distributions to remind you basically how non-parametric versus parametric behave. This is a non-symmetrical distribution because it's non-parametric, for example, as opposed to the normal one. Graphical representations, descriptive statistics only. And here I have a hypothesis testing, which is relevant. Very simple t-test, but every test, really, the process is exactly the same, especially on SPSS. Was staff motivation in the second quarter of 2025 statistically smaller than the motivation measure in the first quarter? You structure the hypothesis, the null hypothesis versus the alternative, and you calculate from the output. I included here the SPSS output for 30 observations. You compare the the t-statistic that was calculated with the t-critical from the statistical tables, and you make a decision, basically. These are the tables, just to remind you. Regression analysis, I'm referring now to the stage 2 of the process. Stage 1 involved the preparatory work I mentioned before, structural equation modeling, the SIR, complexity theory, the simulation models. We discuss the deep learning, the other models associated with the stochastic approaches, the decision tree, etc. All of those are really changing the paradigm. So they have to precede. It's the stage 1 of the process. And now we can apply the classical statistics, hypothesis testing, multiple linear regression, analysis of variance, etc., in order to make the final decisions. But reaching this point, you can safely say that I can deal with cross-sectional data which you collect at a very specific point in time, and still get efficient results, still get causal relationships. This is the most important for us, to improve the value of model specification when it comes to the classical statistical methods, not to invalidate classical statistical methods, but actually to introduce state-of-the-art paradigms which could enhance their validity. And here I have the multiple linear regression with 5 different explanatory variables. And the example, you can see how the data actually behave. This is the regression line as a vector. The black dots represent the observations, and we have basically a thicker line demonstrating that we have a good fit of the observed and the predicted observations, the predicted represented by the red line. Okay, so one of the most important restrictions were the stage one approach, as I mentioned before, will help us is the satisfaction of the assumptions of linear regression. The assumptions are really important in order for our results to be reliable. Those assumptions are difficult to satisfy in most cases. With a stage one introduction, this is going to be much easier. Linearity is the first one. We need to make sure the relationship between the dependent and independent variables is linear. The second one is to ensure that the independent variables are fixed, they are not changing. We don't have autocorrelation. We need to make sure that the dependent variable is going to be autonomous. It doesn't have a dependency on previous years, similar, the same variable. Heteroscedasticity, we need to verify that we don't have heteroscedasticity, which means that the variance of every independent variable, is going to be the same, identical for all different independent variables, and eventually the normal distribution of the error factor. So the idea is how to achieve that. Okay, the OLS is the ordinary least square. Nowadays we have this readily provided from statistical packages, but it's good to know what exactly we're doing, trying to minimize the sum of square errors. And here I have a comparison between the logistic just to demonstrate the difference. The logistic deals with probability 0 to 1, whereas the prediction range for the linear is minus infinity plus infinity. So that's why we need to be careful with the interpretation. Okay, so let's see the example. Dependent variables sustainability, independent variables fair trade, R&D, environmental performance, net exports, and change in education expenditure. All of the data in macro business level, macroeconomic level were taken from international organizations, very valid and credible data. And basically what we try to do is to see how businesses, the business sector, will behave in terms of securing sustainable outcomes over a period of time. So we consider the 5 explanatory variables, and here I have how the variables are symbolized, basically, and the commands for SPSS and Excel. You can use data or other package, doesn't make a difference. The output appears here. As you can see from the statistical significance, we only have 2 variables to be statistically significant. I would say only the R&D is actually statistically significant. The environmental expenditure appears to be marginally 0.06. The p-value is 0.05. But given the small sample, we can accept it. The R-square demonstrates the predictive capacity of the model. 0.6 is acceptable, but for a small sample, but usually we need it to be more than 0.7. The first thing you need to do is to consider visually those independent variables. For example, here I have the R&D and the fair trade. You can see the fair trade extreme values in all different areas. It doesn't, if you take a spiral, it doesn't, you cannot take them with you, which means this is not a good fit, and it demonstrates statistical insignificance, whereas R&D demonstrates significance, because if I take a thicker line here, a spiral, I can get with me all of those dots, and that indicates the trend. It's very similar, so it's a good fit. With a larger sample, those will be much closer to the line. Estimation, very important. What does it mean to have a 0.34 coefficient for R&D? It means that for every 1 unit increase in research and development, the sustainable performance is going to increase by 0.34 units only. So this is important. Let's put it in perspective. If we have 100 British pounds increase in R&D, we'll only provide 34 increase in average sustainable performance of businesses. That is important. It demonstrates how difficult it is to transform research and development into actual productivity. This is really important. This is even worse when it comes to environmental expenditure, green policies. we have 0.02, which means for £100 investment, you're only getting £2 increase in the average sustainable performance. So you can see here, the interpretation is really important in these terms. Then we need to consider the assumptions before closing. Normality is the first thing we need to do. We get the histogram just to demonstrate. It seems for a small sample that is okay. It does follow a bell-shaped distribution. Obviously, there are more rigorous tests to validate this, but more importantly is to check heteroscedasticity and autocorrelation. If you have a heteroscedasticity, you cannot proceed with the results. This is critical. That means essentially you need to check that the variance of all independent variables is similar, identical, following a normal distribution. The JARC-VERA test is really available on SPSS. You can use it. The underlying function is here. The skewness deals with the difference between the median and the mean, and the kurtosis is about the tails of the distribution, how fat or thin they are compared to the normal distribution. You calculate the statistic, and then you compare it with the equivalent tables, and you get the results. You make a decision where you have heteroscedasticity or not. And in a similar fashion, you are considering the Darwin-Watson test for autocorrelation. We don't want our dependent variable to have dependencies on the past or previous years, right? So what we need to do is to verify this. We are using the Darwin-Watson test. Again, in the same fashion, we are formulating the null hypothesis, the alternative hypothesis. Then we calculate the statistic, we compare it with the equivalent tables. Here we have an upper and lower value, and we want our statistic to fall within that range in order to actually say we don't have autocorrelation, to basically to not reject the null hypothesis. Okay, and that means we finish with this particular webinar, and I would like to get some questions from you now. I know I tried to cover a lot of things, but the idea really was to try and introduce you to some state-of-the-art methods currently, which are people attempt to integrate them with existing statistical methods rather than actually changing the methods themselves, which is really a new paradigm in terms of how we can optimize the results and how we can become more efficient during the statistical estimation.
Donis, a couple of people had to drop out. A few moments ago, but
questions.
Any questions?
No question.
Any questions?
Thank you very much, James.
Okay, well, thank you, Adonis. That was very interesting.
Thank you, Adonis. That was very interesting.
Thank you very much. It was nice to see you again, Martin. Thank you, everybody, for joining. If any people have any questions, if they see the recording later, Martin, please share my email with them, and I could respond.
Thank you so much. Thank you.
Okay, thank you.
Thank you. Thank you, everybody. Bye for now.